the next data structure we're going to talk about is something called a heap. It's an interesting data structure. It is, well, so we'll talk about the heap, we'll talk about an array-based implementation, and then, this is kind of giving it away here, we'll talk about how we can use a heap to implement a priority queue. So, a heap is a tree. It's a complete binary tree. What does complete mean?
Filled in. Nothing more.
N one is full.
What's that?
N minus one bubble is full, and then it's also full from left to right.
Right, that's right. So if I have a height h tree, then to level h minus 1, it's full, and then at level h, it's filled in from left to right. So that's what complete means. So a heap is a complete binary tree. Binary, of course, means two children, at most two children. And that tree is either empty or the root contains a value that is greater than or equal to the values of its children, and each child is itself a heap.
So a heap within a heap.
So heap within heap. That's what all trees are, right? Trees are trees within trees, right? So this is an example. Here I have a heap. Binary tree, we agree it's binary, right? None of the nodes have more than two children. Is it complete?
No.
It is.
Yes.
Because the height of this tree is 3, so to level 2 it's full, and at the third level it's filled left to right. So it is a complete tree. Now, the other rule is that it has to either be empty, which it's not, or the root has to be larger than the children. Is 10 larger than 9? Yes. Is 10 larger than 6? Yes. Great. And each of the subtrees, each of the children is itself a root of a heap. So let's look here. 9. Is 9 larger than 3? Yes. Larger than 2? Yes. So this is a heap. This is also a heap. 6 is larger than 5. So this satisfies this is a heap. Okay? This is what we'd call a max heap, which is the maximum values at the root. This is a different one. This is the same values, but this is a min heap for the smallest values at the top. All of the algorithms are the same for max or min. It's just whether you're doing a greater than or less than check. So I'm just going to talk about always as a max heap, but it really makes no difference. Now I want to point out, is this a binary search tree?
No.
So it certainly is a binary tree. And it's not a search tree. Why do you say it's not a binary search tree?
Because
The 9 is larger than the 6.
Yeah, 6 is less than 10.
Right, 6 is less than 10, 9 is less than 10, so these would both have to be on the same side of that node, and they're not. So, big important thing to notice, a heap is not a binary search tree. And just so you're not confused, the assignment that we're doing is not a heap either, the programming assignment, okay? I realized as I was going through this that you might have thought, oh, he secretly made it a heap. I did not. It is not a heap. Okay, so anyway, for the binary, this is not a binary search tree. What relationship do we know about the nodes in this tree? There's only one thing we know, and what is that?
10 is
higher
bigger?
level is bigger than the lower levels.
Not quite. We can be more precise. You were saying?
Well, the high stuff is on the top.
The highest stuff is on the top. We can actually be more precise than that.
The leaves are smaller than the parent.
Yes, but we can be more precise than that.
Oh.
How much more precise
The
can
most
you get?
precise we can be is the largest node is on the root. You said the smallest stuff's on the top, that's true, but this is like the or the largest.
Logical conclusion.
Yeah, but we just go all the way, right? So the largest element in a max heap, the largest element is always at the root. Okay? What do we know about the children? About the order for the children?
Left is bigger than the right. Your
So,
right is bigger than left.
do we know that the right is bigger than the left?
No. We do know that each layer, the children of that layer are less than all of the nodes of the layer we're talking about.
But yeah.
No, we don't.
In the max tree,
So this 5,
5 is less than both 9 and 6.
but it wouldn't have to be actually.
We just know it's
Mm.
okay, well.
It's a
it's less than
coincidence.
The
The
children
only
are
thing
less
we
than-
know about the children is, yeah, we know that every child is less than its parents, so maybe we would get that property you're talking about, I have to think about that a little bit more. But the sibling relationship, we know nothing about.
Mm.
Left and right, we know nothing. So that means that we can't say, like, you remember with the binary search tree, we could always say, all right, if I go to the left child and go far right, that's the largest possible value or smallest possible value in that subtree. We don't have any of that kind of relationship here. The only thing we know is the top value is the largest, and then these are all heaps underneath there too. All right? So this is what the ADT would look like, you know, with all the is empty, get number of nodes, all that kind of stuff. So, how would we implement a heap? Our first thought might be, well, we're just gonna do it as a binary tree. I'm gonna make nodes, and the node will have a value in it, and I'll have two children, and 2 pointers, so they're children pointers, and I'll just keep doing it that way. And yes, you could do that. It turns out there's a much more efficient way to do this. One of the properties of a heap is it is a complete tree. Again, it means that it's full to h minus 1, and in level h, it's full left to right, or it's filled in left to right, okay? So, I want to get a decent marker. This blue one's not. It's okay. So in a complete tree, like that one, I'll say Jane, and then we have what? Bob, Alan, Alan, and Lisa. And over here we've got Tom and Nancy. Okay, so in this tree, this isn't a heap. It's just a complete binary tree. We're going to number the nodes. 0, 1, 2, 3, 4, 5. Now, I numbered these in this way on purpose. I can take each of these nodes and put them in an array. And in the complete binary tree, I can say that if this is node n, the left child is going to be located at 2n plus 1, and the right child is 2n plus 2. So, if node is at 0, 2 times 0, 0 plus 1 is 1. 2 times 0, 0 plus 2 is 2, so 1 and 2. So I can put Jane as my root at 0. Then 2n plus 1 is Bob. 2n plus 2 is Tom. Now let's look at Tom. Tom's node value is 2. So its child would be 2n plus, its left child would be 2n plus 1. 2n is 4 plus 1 is 5. Right here. So Nancy. Bob is 1. 2 times 1 is 2 plus 1 is 3 plus 2 is 4. So 3 and 4. I get, I can't read my writing. Alan. Alan and Lisa. Okay? Now, that's all fun, great, but notice that I don't have any pointers. I can just do basic math. If I want to start at the root, I start at 0. Then I want the left child, 2 times 0 plus 1 is 1. I want the left child, 2 times 1 is 2 plus 1 is 3. I want the left child, 3 times 2 is 6 plus 1 is 7. That would be this one. So I can just do basic arithmetic to find whatever child I want to go to. I don't need to actually follow pointers. Don't even have to have pointers. Okay? That's nice. What else is nice about this is over here. When I want to add a node to this, where does it go?
6.
It has to go
6.
here, doesn't it?
Mm-hmm.
Because this is a complete tree. So it would go here. Where is that in the array? It's right here. If I want to add another node to this, where does it go? It goes hanging off of the left of 3. 3 times 2 is 6 plus 1 is 7. It goes in slot number 7, which is right here. So if you see the pattern here, every node I add just gets added to the end of the array. So as long as I have a complete is the key point here, a complete binary tree, then the next place for a node to go is at the end of that array. So I keep this array, I keep another variable like called end or something like that. That is just the index. In this case, before I added, well, after added these two squiggles, the index, it's 8. That's where the next value would go. Okay, so does everyone understand this? This is a pretty efficient way of implementing a complete binary tree. So remember 2n plus 1, 2n plus 2. Those are the left and right child. Okay, with that in mind, we're going to start talking about some of our heap-based operations. So, first one I want to talk about is remove. So here's my heap, and I want to remove an element. Now, in this case, I'm choosing to remove 10. Removing the root, which is actually what you do most of the time, because that's the only element you know anything about. The only thing you know is the root element is the largest in the heap, so that's the only one you're interested in. You don't know anything about the rest. So how am I going to do this? Well, I just removed that. Now I have 2 disjoint heaps. That is 2 separate trees, but each of these trees is itself a heap, right? Because we know that all the children of the root have to be heaps. So we've got 2 separate heaps. That's not what I wanted. I want 1 heap. So next, what I'm going to do, well, I guess is I'm going to take the last node. Remember, this is the complete tree, so I'm going to take this last node and I'm going to make that the root. Now, I'm not done, I know that, but I'm going to take the last node and make it the root. And the reason I'm doing this is not because I know, well, this is the smallest thing in the tree or anything like that. The reason I'm doing that is I want to keep this complete. So I want to chop that off so I'm still complete. So I'm going to chop that node off, I'm going to put it in the root. Okay, now, I'm not a heap. This is what they call a semi-heap. I've never really paid much attention to this term, but I think what that means is the root is not a heap, but both children are heaps. But I really don't care much. It's just, I know I'm not done yet. So I took the last spot, 5, and I moved it to the top so that I'm still a complete tree, right? This has the shape of a complete tree. But again, I'm not done. What I'm going to do, it kind of makes sense. Well, what about this violates the fact that it's a heap?
That 9 is below it?
Yeah, some of its children are higher than it, right? And I can't let that happen and still be a heap. So what I'm actually going to do is I'm just going to pick the largest of the 2 children and swap them. I swap 5 and 9. Now, from this point of view, since I took the larger of these 2, I'm guaranteed that this one is smaller. So I can ignore the rest of this. This was a heap before, it's still a heap, and it's also smaller in the root. So this half is heapified. This half may not be. In this case it is. But this half may not be. Instead, now I'm going to start here and say, all right, is 5 larger than both of its children? If it's not, I pick the largest of the children and I swap it. And I keep doing that all the way until I hit delete. Notice I'm not adding any nodes here, so my tree is not going to lose its shape. It's still going to be a complete tree. I'm just going to swap. You think of it as I'm just going to have the light item fall all the way down to the bottom until it gets to a point where everything below it is smaller than that. Does that make sense?
Mm-hmm.
So again, in a nutshell, the way that we do the way that we remove an item is we go ahead and we're only removing the root. We remove the root, or we take the last item in the tree, which is the rightmost item on the bottom layer. We put that, overwrite the root element with that, and then we do trickle down swapping until you're always swapping with the largest of the children until we're at a point where both the children are smaller than me. Okay? Now, if I am doing this, let's walk through this with the array, just see how the array helps us, all right? I'm going to delete 10. So it's hard to see maybe from the projector, but these are actually different colors. These are white, this is a light blue, this is a darker light blue. And so we're removing the 10. So first thing I'm going to do is I'm going to take the last element, which just conveniently happens to be right here at the very end of the array. I'm going to move it from there to there. So I copied it up there. When I copied it, of course I just copied it, and then remember that little variable I have over here, my end variable, I decrement that. And so now I know that instead of 5 here, 6 was my end or my next spot. Now 5 is my next spot, so this spot's now free. All right, so I copied 5 up there. Now I have to do the trickle down. So 5's children, this is 0. 5's children are at locations 1 and 2. Which of those is larger? 9. Swap 5 and 9. Swap 5 and 9. Now I'm at this node here, and I look at its children. 2 times 1 plus 1 is 3. 2 times 1 plus 2 is 4. So 2, 3, and 4. Both of those are smaller than 5, so I'm done. So I don't actually have to follow any pointers. It can be a recursive solution. It doesn't really have to be. You could do this iteratively because you're just going through this array, and you could have some condition while I swapped last time, because once you don't swap anymore, then you're done. So while I swapped, check this guy against both children, see which one to swap it, set the flag that I swapped, go back to the top of the loop, do it again, and just keep doing that until you get all the way down, until you don't do any more swapping. Does that make sense? So that's one of the nice things about doing this as an array, is as an array, I don't really need a recursive solution. If I was using this with pointers, tree nodes and pointers, since nodes do not have a parent pointer, I would probably, well, I don't think I need a recursive solution. I might.
Not for real.
Because I don't have to ever back up. I don't know. Okay, so the array one, though, is almost always what people do. Okay, what about inserting? So inserting, opposite of removing. Now, in this case, I've got my starting tree, 95632, the same one that we were left with after removing 10. I want to insert. I'm going to insert 15. So remember, I have to keep the shape of the tree. It has to stay complete. So I'm going to insert 15 right here in the next available slot, left child of 6. All right, that's what I've got here. Now, is this a heap?
Mm-hmm.
No, it's not, because 15 is the largest element, and so we violate our rules, right? So 15 is larger than its parent, not a heap. So, well, how are we going to fix it? Well, the way we know we just added 15, so the way we're going to fix it is 15 is going to look at its parent and say, am I larger than my parent? If so, I'm going to replace my parent. I'm going to swap with the parent. So we do the swap. Now 15 says, okay, am I larger than my parent now? Yes, I am, so I swap. 15 says, I'm the root, king of the mountain, game over, and now we are a heap. So it's really kind of the converse of when we remove. Remember, when we remove, we take something from the bottom, we put it at the top, and then we let it float down to see where it stops. And with this one, we insert at the bottom, and we let it float up and see how far it goes. Okay, makes sense? So, the heap structure is really, it's a simple concept. It's just a binary tree, complete binary tree, where the top element is the largest or the smallest, but it's the same thing. Where the top element is the largest, and the algorithms for inserting or removing are actually pretty straightforward, especially when we use the array-based implementation. If you use the pointer-based implementation, the algorithms really aren't much harder, but they're a little more tedious to deal with. Okay? So, when would we want to use a heap? Well, so I actually am not going to go through any of this code because you guys can see it and we've talked through it. Yeah, I know, we did that. We did that. I don't know why we have to go through that again. So we're not. Alright, so when would we use a heap? Well, a heap would make a great data structure for our priority queue. Right? Because remember the priority queue, the key point is items come in, but the thing that goes out is the thing with the highest priority. And so I could just use a heap and scratch off the word heap and replace it with priority queue, and I'd be done. I can insert stuff in, and whatever I insert in, we know the most important thing will end up floating to the top. And when I want to remove from my priority queue, I just take the root off of the heap. So a heap makes a very simple implementation for a priority queue. I mean, there's really nothing extra to do. And again, using our array-based implementation or representation for the heap, it makes this whole thing relatively simple. Okay, I'm skipping the heap sort. Well, I can talk about it a little bit. Next week we'll cover the sorting algorithms. I think of heap sorting as cheating. So sorting is, I'll give you a brief overview. Sorting is we take a bunch of elements and we put them in order. Okay, that's what sorting is for these purposes. So how do we sort with the heap sort? Well, it's actually pretty simple. You insert all the elements into the heap and then you take them back out. And they're sorted.
Whatever value you set.
Yeah. So like I said, it feels like cheating to me because you didn't really do any work.
Too long.
I just throw them all into the heap, and then I'm guaranteed that the top element is the largest element, so I just pull that out, then I pull the next one out, then I pull the next one out, I just keep pulling them out until the tree's empty. So, like I said, it doesn't feel like I did any work, because the heap is doing it all.
Sounds good to me.
Still logging.
Yeah.
Yeah, it's like, well, technically you wrote it, so
Yeah.
you did work, just not that much.
So it becomes an in log n algorithm. There's n elements that you have to throw in the heap, and each time you do that, remember the worst case scenario is you put something in the heap and it has to go all the way to the top. The height of the tree is log base n of the elements you're in. So n elements times log base n operations. And then removing it is the same. It's a log base n operation for n elements. So your heap sort becomes an n log n algorithm for sorting, which is actually pretty good. We'll do sorts next week, and you'll see when we talk about some of the other ones how much more complicated they are, and you realize why I think that heap sort is cheating, because it's just too easy. All right, so that was it for heaps. We're doing good on time. This will give us enough time to talk kind of in detail on graphs. Also, I mean, we might end a little early today, but that would just be because I think your brains are full, because there's a lot of stuff that we're going over, and it's kind of high. It's very dense in terms of the material. So before we move on, heaps, priority queue.